Okay, so we are going to continue that case of the delta function. So the delta function, well, and so the delta function, well, with the potential energy as a delta function, the Dirac delta function, with some amplitude alpha, and it's pointing in the negative direction. It's going to minus infinity. So we can sketch this potential like this. It is zero everywhere on the negative side. Right at position 0, it goes to minus infinity, and then it's 0 everywhere, also on the positive side. Okay, there is already a video available for the case where the energy is negative, which means bound state. This video is going to be about the energy being positive, which is the case of scattering state. To have a scattering state, what we need is either the energy is larger than the potential at minus infinity, or it is larger than the potential at plus infinity. Well, we have both cases. The energy is larger than the potential at both cases, plus infinity and minus infinity. So we are indeed dealing with the case of scattering states. All right, just as what we did for the negative energy for the bound case, we are going to split the space into two regions. Okay, the one when position is negative, the one where position is positive. Before doing anything, before moving to the math, before writing equations and trying to solve equations, let's think a little bit. Let's think about whether these regions are classically allowed or classically forbidden. Well, region 1, what do we have? Energy is larger than the potential. Good. The particle could be here even if it was a classical system. Okay? This is classically allowed. Remember, our parenthesis here, in a classical system, the energy, which is given by the kinetic energy, which is always positive, plus the potential energy. Classically, the energy is always larger than the potential energy. Okay, so we are in this scenario. Energy is larger than the potential energy. Classically, it would be allowed. Okay, all right. So coming back to our quantum problem. Same story for the region 2. The energy is larger than the potential. Well, this region is classically allowed. Okay. What do we expect in classically allowed regions? The solution, we know the solution will be sinusoidal functions. Sine, cosine, wave, propagating. We don't need to decay. This is classically allowed region. So, what do we expect for our solution? Sinusoidal functions. Now that we thought about this, allowed region means sinusoidal functions, let's move to the solution. Okay, so we are going to write Schrödinger's equation. There is no potential in this region 1. The potential is 0, so that's what we have. Same story on the region 2. We don't have potential. Potential is 0. This is the equation. We rearrange this equation and we have this. Same thing on the right side. Same thing on the positive side. Okay, now what we are going to do, what we always do, we are going to try to rearrange all of these constants that we have there, which are real numbers, mass, energy, h bar. We are going to try to rearrange them in a single symbol squared. And this single symbol, I'll call it k, so k squared. What do we know about energy here? we said the energy is positive. So the energy is positive. That means for my k squared to be positive, I'm going to select all this, not the sign. The negative sign stays out because this whole thing is positive. Okay, same thing here. Since the energy is positive, I'm going to select this piece. This whole piece is positive. I can call it k squared. Okay, so this is the equation now that we have to solve. It's a simple equation. Notice that there is a minus sign here. Different from the case of the bound state, we have the minus sign here. Because we have this minus sign, what is going to be the solution here? Sine and cosine. If I do the derivative of the sine and cosine twice, I get a minus sign. Yeah? Well, but what do we know? I can write sine and cosine, or I can write exponential with I, because exponential with I is cosine and sine. We already discussed this. So when I say sinusoidal functions, either we write directly with a cosine and sine, or you write with exponential with the I. Either solution is correct. I'm going to write here for the region 1, I'm going to write the solution with the I. Exponential of plus ikx and b exponential of minus ikx. On the positive side, same thing. I'm going to write it as f exponential plus ikx plus g exponential minus ikx. Either solution is correct. Okay, so coming back, if I write like this, we are good. If I write like this, it's also correct. The equivalent, we can show that one can be written as the other. Okay, so both are possible solutions. What you need to choose now is which one is more convenient for the problem that we are solving. Since this is a problem of scattering, we'll be thinking about waves moving and being reflected and being transmitted. In this case, it is more convenient to write as I did with the exponential with the I. It is more convenient than writing in terms of cosine and sine. And I'm going to explain to you now why it is more convenient. Okay? Well, we just said exponential with I means sine and cosine. Okay. Now let me pick one piece of these solutions. Let me pick, for example, the piece with ikx. Okay, plus ikx. What we want to do eventually is to include time. This to have the full wave function, the solution for the time dependent Schrödinger's equation. How we include time? By adding here the exponential with the energy. Okay. Well, what does it mean? What is this exponential telling us? As we said, this is a combination of cosine and sine. Let me have a look. Let me try to plot the cosine, for example, the piece of with the cosine. Okay, so if I want to plot this, you see that my plot will depend very much on the time that I select. So let me make the plot first for the case where time is 0. See? So when time is 0, I'll be playing with the cosine of kx. So I'm going to be making this plot as a function of kx. So when kx is 0, my cosine is 1. And then I have my cosine function. Okay, now let me make this same plot for a time a little above 0. Okay, so a different time that is not 0 anymore, it's a little above 0. So now I'm going to deal with the whole cosine, including that piece that involves time. So where is our cosine now going to be 1? Where this whole thing is 0. So it's going to be 1 when kx now is a little shifted. It's not at 0, but at e time over h bar. So it gets shifted. So if I make the same plot, you will see that it is shifted to the right. And if you look at a time even later than this time that we picked, you will see our function. So what we see is that the function is moving to the right. Okay, all that to say that the piece of our solution that has plus ikx, when we include time, that is the piece of the solution that is moving to the right. If you do the same exercise that we did here, you will see that the piece with the minus ikx is the piece moving to the left, to the negative x. Okay, why is this important? Well, let me put what we discuss here. This part with the plus is the one moving to the right. The one with the minus is moving to the left. On the other side, this f is plus ik, so it's the one moving to the right. And the g would be the one moving to the left. Okay, why is this important? Well, writing with exponential of I can distinguish these parts, and this is going to be very important in our problem. I'm going to show to you right now why. Let me bring back our plot here. Okay, so what we said, the part with this plus ikx is the one moving to the right, b is to the left, f is to the right, g is to the left. Now, when we are thinking about a real problem, we have to start it at a certain point. So we usually think, for example, that we are throwing our particle, we are starting our motion somewhere far away, close to minus infinity, where we throw our particle to the right. Okay, so if I assume that I started my motion at minus infinity, and my wave is propagating to the right with this. So the part that is propagating to the right is that one with the plus ikx. It's propagating to the right, it's propagating to the right until we reach this position x0, where there is something, there is some obstacle, there is some perturbation there that the wave will notice, will feel it. When it reaches this point, will then part of it gets reflected because there is something happening there. So this is the B with the minus ikx. Okay, part of it gets reflected, but part of it gets transmitted, and that's the F part gets transmitted. Okay, so that is the F with the plus ikx. It is transmitted and it keeps going to the right and it keeps going to the right, and that's it. There is nothing in that positive region to reflect it. So even though this part is correct mathematically, it doesn't exist physically once we assume that we started our motion minus infinity. Okay, so that's the point. Whenever we are dealing with scattering scenarios, we are always assuming that the particle was thrown, started the motion somewhere. We usually start at minus infinity. And we can then identify which piece is moving to the right, which piece is moving to the left. which piece is moving to the right, and which piece we have to cut out of this story, huh? Because it will not be part. If we write in terms of sine and cosine, it gets more difficult to identify that there is something non-existent in this story. Okay? All right, so now let's put these solutions together. We have for region 1, we then have the plus ikx moving to the right, the minus ikx moving to the left, and on region 2, we have just the part that moves to the right because nothing will reflect it. Okay, good. Now we are going to continue with this problem, see what else, what kind of information we can still get about it. Well, you see, there are many unknowns here. There is A, B, F, and K. Too many things that we don't know. Well, let's play with the properties of these functions to see what else we can do. We know that there are two properties. Now, first, continuity. The wave function has to be continuous. So this is the first property, which in our case means right at 0, we have to stitch the psi1 and the psi2 right at 0. They have to meet at the same point. So in our case here, that means that right at 0, the function 0, the function psi1 has to be equal to the function psi2, which then means that A plus B has to be equal to F. Important equation that we already got. Second property is the story about the derivative being continuous. Well, in general, this is true, except in cases like ours, except where the potential goes to infinity, which is exactly what we have. So we cannot use the continuity of the derivative in this problem. However, it's still worth having a look at what happens to this derivative at x0. Okay, and to do that, we move to Schrödinger's equation, and we are going to play with it a little. So this is the equation. Let me now include here, write the whole thing with the potential. So this is the whole equation. And I want to force the derivative to show up. And I want to force this delta function to finally play a role because so far it hasn't done anything. So for that, what we are going to do is an integral of this equation. So I'm going to integrate everything here. And we are going to integrate very close to that position 0, the special point where the delta function finally does something. So we are going to do this integral at the vicinity of 0 between minus epsilon and plus epsilon. So this epsilon is a tiny, tiny number, it's an infinitesimally small number, almost 0. Okay, but one negative, one positive. All right, so let's solve these integrals. From the first term, what will survive there? The integral of the second order derivative will be the first order derivative. Right at plus epsilon minus what we have at minus epsilon. Okay. Second term, finally the delta function is doing something. That integral, we finally see the effect of the delta function. That integral is 0 everywhere except at the position 0. That's where the delta function is not 0. So what we get there is the function at 0. And then comes the right side. Well, the right side is an exponential of a function. What is exponential of is the integral of a function. What is the integral of a function? Is the area underneath. But the area that we are computing is tiny, tiny, because this epsilon is infinitesimal. So this area is practically zero. So we say that this is zero. All right, let's continue. Now we have to do the derivative on the positive side. Let me write what was the function on the positive side was this. Okay, so the derivative of that give us ik and the function at plus epsilon. Okay, now we are done with this part. Derivative of the negative side. The negative side is the one that had two pieces. No? Okay, careful, don't forget we have this minus sign, so I'm going to include this minus sign. The derivative of both terms gave us ik, okay, but here I have a exponential of ik minus epsilon. Now, when we do the derivative of this, there is a minus sign here, so I'm going to write it here. Okay, and this whole part here, I'm now going to pass to the right. So it becomes equal to alpha plus alpha because I moved to the right. And the function right at zero. I'm going to pick this point, this function here, and write it right at zero. So it's just a plus b. Very good. So now let's continue. Let's have a look at what we have. Well, remember, epsilon is infinitesimally small. Epsilon is zero. So we have here exponential of zero is 1. Exponential of 0 is 1. Exponential of 0 is 1. Okay. And I'm going to pass this whole thing, this h bar squared to m, to the right. Okay. So I have ik f minus a minus with minus plus b, and I passed that 2m and everything to the right, so I have minus 2m alpha h bar square a plus b. Okay, one more step. I'm going to pass now this ik also to the right. Okay, so I have f minus a plus b equal to minus 2m alpha h bar square ik. Well, but parentheses here, 1 over I, no, I in the denominator can be brought to the numerator with a minus sign. Okay, so I'm going to get rid of this I here, bring it up with a plus sign. Okay, good. Now, the only thing that is a bit annoying here, there are too many symbols in this story, M, alpha, H bar. Well, let me combine them all in a single symbol so it gets easier to write things, okay? All right, so we're almost done. I can now write this equation like this. If I pass a to the right, I have a and then 1 plus 2 beta I. If I pass b to the right, I get a minus b, 1 and minus 2 beta I. Okay, so I have this equation using this relationship between the derivatives of the functions, huh? And I have this equation. Let me bring it closer to us. That's all. And remember how many unknowns we have. A, B, F, K. I cannot do much more here. Huh? But there is still something good that comes out of this story. So we are not going to find a wave function, normalize. We cannot even normalize this wave function because we have exponentials with I cannot even normalize this function. So we reach a point that that's all we have, but what we have here can still give us some useful information. What is that? Well, remember that we are saying, let's come back to our drawing here. This part with the plus ikx is what is moving to the right. Is the part that was the beginning of the story when we threw our particle to the right. That's how everything started. Well, now, once we reach this position 0, where we have that delta, part of it gets reflected, part of it gets transmitted. We can ask ourselves, how much gets reflected? How much gets transmitted? So this question that I'm just talking about, that we are asking here is, how much gets reflected is what we call the reflection coefficient. And we are talking about probability, we're talking about quantum mechanics. So the reflection coefficient is the absolute value square of B over the absolute value square of A. Now from everything that we threw that is contained in the A, how much gets reflected? Okay. And we can also ask about the transmission coefficient. What is the transmission coefficient? Well, from everything that we threw, that we started the motion from, how much got transmitted is contained in the F part. Okay, so these two things we can compute based on the two equations that we have, this equation 1 and this equation 2. So how are we going to get, let's start with the reflection coefficient. How are we going to get the reflection coefficient? Well, I need to get rid of F because F is not in the story of the reflection coefficient. So we are going to combine these two equations, and instead of putting F, we are going to write A plus B equals 2. We have A plus 2 beta IA, and then we have minus B and plus 2 beta IB. I wrote all this to make it easy to see how we can simplify things. So A is gone, and I'm going to bring everything that depends on B to the right side. So you see that we have this B with this B. This gives us 2B, and we have this other term that gives us minus 2 beta IB. All that equal to 2 beta IA. What I'm trying to do is I'm trying to write B as a function of A to then bring it back to this equation. Okay. Well, do you see that number 2 is everywhere now, so we can get rid of it. And then we find that B is then I beta A, and in the denominator 1 minus I beta. Okay, great, because now we can go back to that equation for the reflection coefficient, absolute value of B and absolute value square of A, and put this. All right, so what is the absolute value square of B? Is the absolute value square of this and of this. absolute value square of I is 1. So we have here b square, beta square, and a square. And in the denominator, we have 1 plus beta square. If this is not yet, uh, if this doesn't come quick to you, well, let's show. So this is what is in the denominator. So what is absolute value square is the conjugate, complex conjugate, and the function. And if you open all that, you will see that we just get 1 plus beta square. You have 1, then minus I beta, plus I beta, and plus beta square when I multiply these two. So that's the answer. Okay, so then I come back to our reflection coefficient. I'm going to write what this B, absolute value square of B is beta square, absolute value square of A, 1 plus beta square. This is this whole thing here is the absolute value of B square, but remember there was an A square. So we got this. Okay, so this is our reflection coefficient. Very good. Now let's move to our transmission coefficient. The transmission coefficient is this. So now we want to write F as a function of A. And let's see what are the equations that we have. We want to write F as a function of A. Well, how about we look at this equation here? And because we already know B as a function of A. Okay, so let me put here F is A plus B. But we already found here. So let me copy this whole thing. We already found what B is. So now I can write F as a function of A only. A plus I beta A 1 minus I beta. So I have to put everything under the common denominator. And then we have 1 minus I beta plus I beta A. And you see that F is A over 1 minus I beta. So then our transmission coefficient is going to be 1 plus beta square. Very good. Okay, so this is very interesting. We got that. Beta, we'll come back to this beta, but beta is where the energy is. So we can say whether the reflection, so the reflection and the transmission will depend on energy. So we can see which one is larger, which one is smaller, depending on energy. But before we move into that, look at these two results that we have. This is very important what we have here, because you see that the reflection coefficient plus the transmission coefficient, if you plus reflection plus transmission, this is equal to 1. It could not be anything else. Either you get reflected or you get transmitted. There is nothing else to happen here. So the sum of all of these probabilities has to be 1. Okay, excellent. So now let's just come back to what we were talking about. We said that inside this beta, we have energy. Let's go high up to see where we had defined this beta. So here is where we define beta. So it depends on K. But remember, if you go high up, you will see that K is related to energy. Okay, I let you put all these things together because this is just algebra. Just have to be careful. if you do all this, put all this together, you will finally be able to write the reflection coefficient and the transmission coefficient in terms of energy. So let's just put the solution here. I hope you will do it. And so the reflection coefficient has the energy appearing here. The transmission coefficient has the energy appearing here. All right. Okay, so this is the reflection coefficient, does depend on energy, and the transmission coefficient, which of course also depends on energy. What does it mean? Let's analyze two different cases, two different extremes here. Okay, so again, let's remember, we have here our potential. If the energy is huge, so let me try to exaggerate things here. If the energy is enormous, far away, far away, what is going to happen to the reflection, the transmission coefficient, mathematically? So if this energy is huge, if I come to the reflection coefficient, I'll be playing with something here that is huge. So this means that my reflection coefficient will become very close to zero. And how about the transmission coefficient? Well, we have 1 plus something that is huge here. So this is going to zero, so the transmission coefficient is close to 1. So this mathematically, but it makes sense. If our energy is so far away from the potential, the particle is coming to the right, and it hardly notices that there is something happening at zero. It just goes through easily. Okay? All right, so this is the case where the energy is huge. Let's see another extreme. Let's get rid of this. And now let's think about the energy being very small. If the energy is so small, there is almost touching there. So if the energy is so small, then what do we have now? Again, let's come to the reflection coefficient. If the energy is tiny, tiny, and we come to the reflection coefficient, we have 1 plus something tiny, tiny. Well, this is approximately 1, while the transmission coefficient is 1 plus something that is tiny here. So this is huge. So if this is huge, well, this goes to 0. Okay, so this is the case where this other extreme case where the energy is so small, almost everything gets reflected now. Okay, so this is pure quantum mechanics. In a classical object, if the energy is here, we just go. There is no region to get for a particle to get reflected. So what gets reflected here is this wave. Okay, so this is the end of this case where we have scattering states for the delta function. Well,